4,800 soldiers evacuated from Normandy beaches in June 1944. 1,340 with traumatic brain injuries from impacts that should not have been fatal. A 28% TBI rate from blunt force trauma. The chief medical officer reports this as acceptable for armored warfare conditions. This was the reality of American head protection in World War II. The solution existed since 1940, but American manufacturers changed one invisible feature that turned German engineering into a skull-crushing disaster that left thousands brain-damaged. July 1944. Lieutenant Colonel Viggo Sorensen, U.S. Army Neurological Services, arrives in Normandy to investigate reports of catastrophic head injury rates in soldiers who survived initial combat. The situation is worse than the Surgeon General imagined. Field hospital neurologists report traumatic brain injuries in soldiers whose helmets show no penetration. War correspondent Ernie Pyle observed, "I've seen boys come off the line wearing intact helmets, walking and talking, who drop unconscious 6 hours later and never wake up. The helmet stopped the shrapnel, but something else went wrong." 1st Army Medical Command estimates 22% of all combat evacuations involve head trauma without helmet penetration. In one documented case at a field hospital near Carentan, 4,800 wounded arrived during June. 1,340 have traumatic brain injuries from concussive impacts. The hospital commander considers this ratio normal for mechanized warfare. The Allies are using helmets soldiers call steel pots, M1 helmets with fiber liner inserts, standard issue since 1941. They stop bullets and shrapnel adequately, but transmit impact force directly to the skull. The liner sits close to the head with minimal suspension. When the helmet is struck by blast, concussion, vehicle collision, or debris impact, the force transfers through the liner into the cranium. Many soldiers survive the initial hit only to develop subdural hematomas hours later. British helmets aren't much better. The Brodie helmet with leather liner. Designs dating back to 1916. Steel shell adequate, but no real suspension system. Impact energy goes straight through. Equipment designed for trench warfare with artillery fragmentation threats, not for mechanized combat with blast waves and vehicle crashes. Sorensen watches soldiers develop symptoms: headaches, confusion, seizures, unconsciousness. Men whose helmets show dents but no perforation, yet their brains are hemorrhaging inside intact skulls. The entire Allied medical system struggles with the one injury pattern that shouldn't exist with modern helmets: traumatic brain injury from blunt force transmission. He sends a cable to Washington estimating 25% of all casualties involved preventable TBI. Years later, in his 1958 Military Medicine Journal article, The Liner That Failed, Sorensen admitted this figure was actually conservative, designed to avoid undermining confidence in Army equipment. Whether 25% documented hospital ratios or that specific 28% rate in Normandy, the numbers are devastating. You don't win wars by protecting men from bullets, but leaving their brains vulnerable to impact transmission. The Germans face no such crisis. Allied medics treating captured German soldiers notice something immediately: remarkably low rates of concussive brain injury in men whose helmets show impact damage. German soldiers survive artillery near misses and vehicle accidents that should cause severe TBI. Their helmets look crude, but function remarkably well. These helmet systems become more valuable than weapons. Soldiers strip them from prisoners. Medical officers study them obsessively. After the fall of Cherbourg in late June 1944, large quantities of German equipment were captured, sufficient to equip a reconnaissance battalion, where, by mid-July, American intelligence officers had begun studying these helmet systems intensively, trying to understand why German head injury rates were so much lower. The Stahlhelm liner system, steel helmet suspension, was redesigned in 1939 by German engineer Klaus Meyerhoff at Tharley Ironworks in Saxony-Anhalt. After extensive impact testing in 1938 to 1939, using cadaver heads and pressure sensors, a trial production of 30,000 units was distributed to Wehrmacht units for field trials. The German Army officially adopted the improved suspension on November 8, 1940. 2 years of biomechanical testing before full implementation. By 1941, the German military had retrofitted hundreds of thousands of helmets with the improved suspension system. Every frontline soldier received the upgrade. Every tanker, every assault infantry unit, every paratrooper. A neurological advantage that would prove critical during the brutal fighting in Russia and North Africa, where blast waves and impacts were constant. The design. The outer steel shell remained unchanged, the distinctive German Stahlhelm shape. But inside, everything was different. That liner suspension would prove crucial. The system consisted of a leather band that ran around the inside of the helmet, suspended by 3 articulating arms attached to lugs riveted to the shell. But the critical innovation was spacing and compliance. The German suspension maintained 1.2 to 1.5 centimeters of air gap between the leather liner and the interior of the steel shell. This wasn't arbitrary, this was calculated. That air gap allowed the shell to decelerate impact forces over distance before transferring them to the skull. Basic physics: increasing the stopping distance decreases peak force. But the real innovation was the articulating arms. Each arm was made of spring steel, shaped into a shallow S-curve. When the helmet experienced impact, these arms flexed, absorbing energy. The spring action converted sharp impact forces into distributed pressure over time. The leather band itself was thick, 6 mm vegetable-tanned leather that compressed under load. The system created 3 layers of energy absorption. The air gap provided distance, the spring arms provided compliance, the leather provided final cushioning. Impact force that would crack a skull hit the steel shell first, dissipated across the air gap, compressed the spring arms, and finally reached the leather band at dramatically reduced intensity. The German technical manual was explicit. Die Federarme müssen beweglich bleiben. The spring arms must remain flexible. Der Luftraum ist kritisch für Aufprallschutz. The air gap is critical for impact protection. Regular inspection. No modifications that reduced the spacing. German casualty studies showed 40% lower traumatic brain injury rates compared to 1939 baseline. The helmet still stopped penetration like the old design, but now also protected against blunt force trauma. Soldiers survived near misses that would have killed them before. Tank crews survived vehicle rollovers. Infantry survived debris strikes from building collapses. In 1940, American military equipment evaluator Major Richard Hayes had been stationed as an observer with British forces. During the Battle of France, he recovered a German helmet from a destroyed tank. The German crewman had died from fire, but the helmet showed massive denting from impact, yet the interior suspension was intact, showing how it had flexed during the collision. Hayes shipped the helmet to Washington with detailed photographs and measurements of the suspension system. He emphasized the spring arm mechanism repeatedly, noting it was unlike anything in American or British helmets. Official records show the helmet arrived at the Army Ordnance Department in August 1940. The U.S. military showed moderate interest. America wasn't at war yet. The M1 helmet was just entering production. The design was already finalized. The fiber liner was already contracted. Changing now would delay production. The German suspension system was filed away as interesting but not immediately applicable. December 1941 changed priorities. America was at war. Head protection became critical. But the M1 helmet was already in mass production. Hundreds of thousands already manufactured. The logistics of redesign seemed impossible. In early 1943, with casualties mounting, the Ordnance Department retrieved Hayes's German helmet and began serious evaluation. They measured every dimension, tested the spring arms, analyzed the leather composition, calculated the air gap spacing, even performed drop tests. Then they redesigned it. American engineers at the Mine Safety Appliances Company in Pittsburgh, Pennsylvania, in mid-1943, created their improved suspension. They retained the general concept, a liner suspended inside the shell. They kept the leather band idea. They maintained the attachment points. What they changed was invisible from outside, the suspension compliance. The German system used spring steel arms with 1.2 to 1.5 centimeter air gap and energy-absorbing flex. The American version used rigid pressed fiber arms with 0.6 to 0.8 centimeter air gap and minimal give. The logic seemed sound. Fiber was cheaper than spring steel, easier to manufacture at scale, lighter in weight, simpler to produce. American manufacturers also simplified the liner band. The German design used thick vegetable-tanned leather. The American version used thinner chromium-tanned leather for faster processing. They reduced the band width from 40 mm to 32 mm to save material. For peacetime use and minor impacts, the design worked adequately. For combat conditions in Normandy and beyond, it proved catastrophic. Lieutenant Colonel Sorensen later wrote with the authority of a neurologist who treated the consequences. Any biomechanical engineer knows that impact protection requires both distance and compliance. Distance alone is insufficient. The suspension must give, must absorb energy, must transform sharp impacts into distributed loads. A rigid suspension transmits force. A compliant suspension dissipates it. The rigid fiber American suspension, when struck by blast waves or debris, provided minimal energy absorption. The 0.6 centimeter air gap was half the German spacing. The fiber arms didn't flex, they transmitted force directly. The thinner leather compressed completely under load, bottoming out and allowing the liner to strike the shell interior. Impact forces that should have been absorbed were instead transmitted directly to the skull. The suspension rigidity was the critical failure. Pressed fiber has no elastic properties. It doesn't spring back. It doesn't absorb energy. In combat impacts, shell concussion, vehicle crashes, falling debris, the rigid suspension acted like a force conduit straight to the cranium. Soldiers survived the initial impact only to develop brain bleeds hours later when the hematoma reached critical size. Production begins. Millions of units manufactured. Every soldier deploying to Europe receives the M1 helmet with fiber suspension. Initially, against bullets and shrapnel, they perform well. The problems only emerge with blast impacts and blunt force trauma. June 1944, Normandy invasion. Soldiers begin arriving at field hospitals with intact helmets but severe neurological symptoms. Medical officers initially attribute it to artillery concussion, standard combat conditions. Blast wave exposure causes TBI regardless of helmet design. But then patterns emerge. German prisoners with similar blast exposure showing lower TBI rates. American tank crews surviving crashes but developing subdural hematomas. Infantry hit by debris displaying symptoms hours after the impact, when they seemed fine initially. Forward neurological units begin documenting cases. Sorensen arrives in July and immediately investigates. He examines both helmet types. He performs comparative impact testing using sandbags and pressure sensors. He finds the German suspension reduces transmitted force by 60%. The American suspension reduces it by 15%. He sends an urgent cable to Washington. Helmet liner suspension inadequate for combat impacts. Request immediate investigation of energy absorption properties. Current design contributing to preventable traumatic brain injuries. The War Department responds slowly. Investigation of what? The helmets stop bullets. They stop shrapnel. What more is required? Sorensen's response is detailed. They need to protect against blunt force trauma, not just penetration. The German design includes compliant suspension with adequate standoff distance. Ours doesn't. Men are developing brain hemorrhages because impact forces transmit through rigid fiber directly to their skulls. The War Department begins an investigation. They pull Hayes's 1940 report. They examine his original specifications. They discover the spring arm mechanism was explicitly noted as the critical innovation. They discover American manufacturers never implemented it. They substituted rigid fiber to reduce costs and simplify production. Why? Manufacturing complexity. Spring steel was needed for weapons. Fiber was available. Assumption that any suspension was better than none. Belief that the standoff distance alone would suffice. A series of cost-benefit calculations that seemed reasonable in 1943, but proved neurologically catastrophic in 1944. The temporary solution? Field modification kits allowing units to pad helmet interiors with additional fabric. Orders to wear helmet liners looser, though this reduced stability. Distribution of medical guidelines for recognizing delayed TBI symptoms. These are workarounds, not solutions. By August 1944, everyone in the medical corps knows American helmet suspension is inadequate. Neurologists write reports. Battalion surgeons document cases. Some units cannibalize German helmets, installing the spring suspension systems into American shells, unauthorized field modifications that actually work. The European campaign continues through fall 1944. Men keep developing preventable brain injuries. Sorensen establishes TBI tracking protocols. He documents impact types, helmet damage, neurological outcomes, mortality rates. He writes weekly reports. He testifies before medical review boards. He demands engineering changes. The response isn't immediate redesign. The response is incremental improvement. The Ordnance Department contracts with manufacturers to develop improved suspension, research into spring steel inserts, testing of various standoff distances, prototypes in late 1944. This takes time, months of testing, production retooling, new supply chains. Meanwhile, men keep taking hits that their helmets can't properly protect against. The fiber liner keeps transmitting forces it should absorb. By spring 1945, improved suspension systems begin reaching some units. Not spring steel, that's still in short supply, but improved fiber with better elastic properties, increased standoff distance, thicker leather bands, better, but not equivalent to the German design. The exact number of American soldiers who suffered traumatic brain injury specifically from inadequate helmet suspension cannot be calculated from surviving records. Medical reports often attributed TBI to artillery concussion or blast exposure, deflecting from equipment inadequacy. What is documented? Over 23,000 American evacuations for traumatic brain injury during the Northwest Europe campaign. German forces showed consistently lower TBI rates in comparative studies. Allied neurologists repeatedly citing inadequate impact protection as contributing factor. Post-war biomechanical studies confirming that compliant suspension with adequate standoff dramatically reduced transmitted force. The German Stahlhelm suspension succeeded because Klaus Meyerhoff and Thale engineers understood that head protection required more than a steel shell. It required physics-based energy absorption, distance, compliance, and progressive loading. The spring arms weren't optional. The air gap wasn't excessive. The thick leather wasn't luxury. Everything served a biomechanical purpose, tested with actual impact measurements. American manufacturers kept visible features and changed invisible ones. They assumed rigid fiber was equivalent to spring steel. What is documented? Over 23,000 American evacuations for traumatic brain injury during the Northwest Europe campaign. German forces showed consistently lower TBI rates in comparative studies. Allied neurologists repeatedly citing inadequate impact protection as contributing factor. Post-war biomechanical studies confirming that compliant suspension with adequate standoff dramatically reduced transmitted force. The German Stahlhelm suspension succeeded because Klaus Meyerhoff and Thale engineers understood that head protection required more than a steel shell. It required physics-based energy absorption, distance, compliance, and progression of loading. The spring arms weren't optional. The air gap wasn't excessive. The thick leather wasn't luxury. Everything served a biomechanical purpose, tested with actual impact measurements. American manufacturers kept visible features and changed invisible ones. They assumed rigid fiber was equivalent to spring steel. They assumed reduced standoff would suffice. They assumed the suspension mechanism's compliance didn't matter as long as something separated skull from shell. They were wrong. Consequences were measured in permanent brain damage. Soldiers who survived combat but lived with seizures and cognitive impairment, and American troops attempting to salvage German suspension components because their own equipment was neurologically insufficient. This is what happens when form is copied but not function, when manufacturing cost reduction is prioritized without understanding biomechanical requirements, when good enough is assumed without impact testing under combat loads. Post-war military specifications eventually mandated compliant suspension systems with minimum standoff distances, effectively abandoning the rigid fiber approach. The modern American combat helmet, from the PASGT to the ACH to the ECH, incorporates multiple compliance layers and significant standoff distance. The principles Meyerhoff established in 1939, impact protection requires energy absorption over distance through compliant materials. The physics of brain protection haven't changed. Rapid deceleration causes injury. Transmitted force causes hemorrhage. Compliance reduces peak loads. These aren't engineering preferences. They're neurological realities that determine whether brains survive inside intact skulls. Military museums occasionally display both versions. The German M40 Stahlhelm with spring suspension next to the American M1 helmet with fiber liner. To casual observers, both look like adequate protection. Steel shells, interior liners, chin straps. The difference is in the suspension arms, in the spring steel versus rigid fiber, in the mechanical compliance invisible to anyone who hasn't studied impact biomechanics or treated subdural hematomas. Lieutenant Colonel Sorensen returned to the United States in December 1945. He was assigned to Walter Reed Army Medical Center, where he established the military's first traumatic brain injury research program. He wrote extensively about combat helmet design, emphasizing that protection required engineering understanding of biomechanics, not just metallurgy. His papers, archived at the National Museum of Health and Medicine, include pressure measurement data, comparative impact tests, and increasingly frustrated correspondence with Ordnance Department officials who resisted acknowledging that American suspension design was fundamentally inadequate for protecting against blunt force trauma. In 1949, testifying before a Senate subcommittee investigating wartime equipment failures, Sorensen stated, "We copied the appearance of German helmet design while omitting the most critical element, compliant energy absorption. This wasn't an oversight. It was cost-cutting and manufacturing simplification without biomechanical testing." Thousands of soldiers suffered permanent brain damage from impacts their helmets should have protected against. We had the solution in 1940. We chose not to implement it properly. That choice had consequences measured in destroyed lives. The subcommittee's findings were partially classified, fully released in 1974. The conclusions were unambiguous. Inadequate suspension compliance, insufficient standoff distance, failure to implement proven foreign innovations completely, institutional resistance to design modifications even after neurological casualties were documented. The German suspension system remained superior through 1945. Only in the Korean War did American helmets finally incorporate truly compliant suspension with adequate spacing. The spring arm principle, or variations using elastic materials, became standard in NATO equipment. American helmet design eventually converged on the same biomechanical principles, but not before thousands learned through brain injury what proper engineering had already established. Vietnam saw further improvements. The PASGT helmet of the 1980s finally incorporated the multi-layer compliant suspension that German engineers had implemented in 1940. The story repeats across military equipment history. Effective foreign design observed, superficially copied, biomechanically misunderstood, casualties resulting, lessons eventually learned. The helmet suspension failure wasn't unique. It was typical of institutional blind spots that assume mechanical substitutions don't matter if the outer appearance matches. Biomechanics matters. Manufacturing cost reductions have consequences measured in brain tissue. Sometimes the best approach is exact replication of proven engineering, including the compliance mechanisms that seem unnecessary until soldiers are absorbing impacts. If this story shows you how mechanical engineering shapes survival, do me a favor, hit that like button. Every like tells the algorithm to share these forgotten biomechanical lessons with more people. Subscribe and turn on notifications. We're uncovering the invisible engineering failures that changed military medicine, one overlooked mechanism at a time. Drop a comment and tell us where you're watching from: the United States, Germany, anywhere with engineers or medical professionals in your community. Our audience spans the globe, and you're part of keeping these hard-learned lessons alive. Tell us your location. Tell us if you or your family served in combat roles. Tell us if you've ever seen protective equipment fail because someone substituted a similar component without understanding the mechanical properties. Just let us know you're here. Thank you for watching, and thank you for making sure these engineering failures aren't forgotten. The soldiers who suffered permanent brain damage from preventable impacts deserve to be remembered, and you're helping ensure their injuries taught lessons that endure. Sometimes, the most important part of protective equipment is the part you can't see. The compliance mechanism, the energy absorption properties, the invisible engineering that separates protection from transmitted force that destroys brains.